Okay, so welcome back. So the next thing we want to do is talk about some translations from English sentences. Now, the problem with English is that sometimes things can be ambiguous. So sometimes when I say a specific sentence in English, you can interpret it in multiple ways, and in fact, you can take the logic out in different ways. When we translate into logical connectives, when we translate into logical expressions, this should not be the case. So the purpose of having logical connectives is that this connective can only be represented in one way. It can only be interpreted in one way. So when we translate these sentences into their symbolic form, what you'll realize is sometimes we lose a little bit of the meaning. So the good thing about English is that it's expressive. We have many ways to say the same thing, and there's some hidden meanings behind the statements. But in logic, there's no such thing, right? So we have the tools like and or and the connectives like implication and biconditionals, but that's about it. So you're going to see this throughout the next two examples here. So let's pretend that we have some primitive statements. And by the way, if you don't remember what primitive statements mean, is that they are in their simplest form. So P, Q, and R here are in their simplest form. So let's pretend that P is you get an A on the final exam, Q is you do every exercise in the textbook, and R is you get an A in this course. So uh, so what if I said something like this? Getting an A on the final exam and doing every exercise in the textbook is sufficient for getting an A in the course, which is probably something I would say. Um, so, how would we be able to translate this into symbolic form, into logical form? So, the first thing we should identify with any of these translations is what are the logical connectives? What words indicate the logical connectives? Well, you can see here that I have the word and, that indicates a logical connective. We also have is sufficient for, right? That is, as we said, another connective that indicates that we have a logical connective. And I think that's about it. So getting an A on the final exam is translated as P. And then we have every exercise, doing every exercise in the textbook is Q. And then we have getting an A in the course is R. Okay, now we can go back in our notes and we can see that the word and is indicating a conjunction. So a conjunction, the symbol looks like this, looks like the uh, upward arrow, upward triangle, and then the is sufficient for. Now this one's a little bit tricky because is sufficient for is an implication. So we have to decide, is the implication going forward or is it going backwards? In this case, if we look back in our notes, the is sufficient for is a forward pointing arrow. So it's P and Q is sufficient for R, is guaranteeing R. Now, the last thing is we can't leave the expression like this. What we need to do is decide which of these expressions come first. So is it here? Is it P and Q? Is it number one or is it number two? Now let's start with number two. Number two says you got an A on the final exam, and if you do every exercise in the textbook, then you'll get an A in the course. Okay, so is that what I'm trying to say in this statement? So a lot of it is your judgment. You have to understand what is this English statement trying to say. So is it saying that you already got an A on the final exam and there's a rule that doing every exercise in textbook is sufficient for getting an A in the course? So I don't think so. I don't think that is what is trying to be conveyed here. Instead, I think what is trying to be said here is if you get an A on the final exam and you do every exercise in the textbook, then you can guarantee the A. So you have to do both of those and then you guarantee the A in the course. Okay, so you have to make sure that if there are different connectives that are joining these expressions together, that you put in the necessary brackets in there. Okay, so the brackets are very important. We can't just leave it open and not use that. Okay, next. Um, you got an A on the final exam without doing every exercise in the textbook. Nonetheless, you got an A in the course. Okay, now just if we take a look again going a little bit faster this time, we'll see that the connectives seem to be that the word we have the word without and we have the word nevertheless. Okay. Now, I know the word nevertheless has some meaning to it, right? In English, nevertheless means that even though this happened, you still got an A in the course. So that's really what's being expressed here. In logic, there's no such meaning behind a statement. So, what is the best translation for each one of these? So, again, you got an A on the final exam. That seems like it's a P. And then every exercise in a textbook, that seems like a Q. And then A in the course is R. So, let's start off with without. Without seems to suggest to you that there is a negation involved. There should be a negation involved. So, first of all, where's the negation? What did I not do? Right. So I think it's not every exercise in the textbook. So I didn't do every exercise in the textbook, but I still got an A in the final exam. Now, without seems to be that it's an and. So we can try out all of the different connectives. Is it or? Is it or not Q? Is it implies not Q? Or is it the biconditional not Q? And I think here without is and not Q. Okay, so again, try to be convinced of that. Now, the next thing I'll say is remember before I said there has to be brackets in order to identify the expression. So realistically, we should have a bracket here just to indicate that not goes with the Q. Now, the thing is that for negations, this is a special case. So I don't really need a bracket here because negations already take precedence over the other connectives. So whenever it's a negation, you don't have to have these brackets in there, although it doesn't hurt to have it, right? So for readability or anything else, it does matter. Okay. The last thing we should answer is what is nevertheless? So nevertheless, is it an or? Is it an implication? Is it biconditional? Is it an and? So I think the best fit here would be an and. Now again, I stress that the word nevertheless, it does have extra meaning, right? It says even though that this happened, you still got an A in the course. But in logic, there's just no way to express that. It's that you got an A on the final exam, you didn't do every exercise in textbook, and you got an A in the course. That's what happened, right? So you lose a lot of the meaning by translating into this symbolic form, but this is nonetheless how we're going to translate it. Now, if you take a look at the expressions here, we have P and not Q and R. So the last thing is, do we need any brackets to indicate which order it comes in? Now, you might argue that there is a period there, so you might say that it comes like this. Now, that's fine, and if you put the bracket in there, that is fine. But just know that whenever we're dealing with the same logical connective, here we have and, it doesn't matter the order, right? So if you think about it, today is Monday, and today is sunny, and today is greater than 6 degrees Celsius. It doesn't really matter in which order I say those things. The logic is going to be exactly the same. If I keep using the and word, the logic is going to be the same. So here I can just as easily leave out any bracket and the logic is exactly the same. That is not going to be the case with this one that we had here. Okay, so if I put the bracket somewhere else, then it changes the meaning of the whole statement. Okay, so if it's this, so once again, if it's the same connective, we can leave out the brackets, but if they're different connectives, then we need them. Okay, so what good is this? What good is translating a statement into symbolic form? Well, one thing that we can identify is we can when we translate things into their propositional form or their symbolic form, then we can start to see what their meaning is. We can start to see what their outcomes are, and we can start to see when it's true and when it's not true. So, for example, let's say I translated a statement that worked out to be something like this. Okay, so we have not P and, we have P and Q in a bracket. Now, I said earlier that the bracket really doesn't matter too much here, but I'm going to put the bracket here nonetheless. And I'm going to draw a truth table associated with this statement. So, what the truth table is going to show me is that what are the cases when this statement is true and what are the cases when this statement is false. So I'm going to start off with the four cases here. Okay, so we have P and Q. So now, I said the negation always comes first. I'm going to put a small bracket there. Again, you don't have to, but you should visualize that that is what comes first. So if we have a P, which is a zero, so P is zero, and what is not P? Well, not P would be one. Okay. Now, what we're doing here is we are identifying each stage of the evaluation of this compound statement. And eventually, we're going to get an outcome for the whole compound statement. So just for not P, the result here is a 1. And again, for this case, it's a 1. So take a look at P. P is 0 in both cases. They are 1s in here. P is a 1 here and a 1 here, and there's zeros over here. Okay. Now, I can now say that the outcome for not P is as follows, is that column there. Okay, what about P and Q? Well, what is the result of P and Q? Now, I'm just going to copy P and Q over. So P looks like this, and then Q looks like this. Okay, so I'm just going to copy those two over. And what is the result when I AND them together? Well, if you remember, the definition of the AND is it is a 1, it is true when both are true and false otherwise. Okay, so it is 1 when both inputs are 1, but it is false otherwise. Okay, so now if I take a look at this column right here, that column represents the outcome of the other bracket. So now we have outcomes for both brackets, right? So we have outcome for the first bracket, and we also have the outcome for the second bracket. I'm going to take these two columns and I'm going to AND them once again. So I'm going to, you see, this is our third step. I'm going to AND them. And the process is actually very similar to math, right? So we start from the innermost bracket and then we work out to the outermost bracket. Right, so this is how we evaluate what a truth table looks like. So here we have an and we're taking this column and we're anding it together. Now notice that in this case that there are no cases where they are both ones. So that the outcome is that they are actually all zeros. So typically what I would expect is somehow make note of uh, this line here to indicate that this is the final outcome. So if we were doing this on a quiz or an exam, it would probably be good to write it on the side here. So this is, I would say this is our final outcome. Right, so I'll say equal, and then this. Okay, so in our in-class, once again, I will kind of go through what I would expect on a quiz, or if you ever encounter such a question, how would you represent that on the computer? Okay, but let's take a look at this as a meaning. So what have we just done? We've drawn a truth table that of this expression, the not P and Q. So think about what the this expression would be translated from. It would sound something like today is not Thursday and today is Thursday and sunny. Now, in particular, I said today is not Thursday and today is Thursday. So is that possible? Is it possible to be Thursday and not Thursday? Well, no. So right there, you can probably convince yourself that this statement, no matter what P and Q are, is never going to be true. This can never be a true statement. And that's what's indicated here. Every single case, whether it's, whatever P and Q are, it comes out to be zero. It comes out to be false. Okay. In fact, if we go one slide ahead, this is what we call a contradiction. So this statement that we just encountered is called a contradiction. So a contradiction is that we have a statement that is always false. Okay, so this is a statement that is always false. So the statement, today is Thursday and today is not Thursday, is always a false statement. Now, what about or? What if I said today is Thursday or today is not Thursday? Well, in that case, it's always true. That's always a true statement. So that is a tautology. That is called a tautology. So try to remember these two. But there is a third definition here, which is called a contingency. Contingency is probably not something that I'll use in this course, but anything else. So when sometimes it is true and sometimes it is false, it is called a contingency. Okay, but usually we use these two terms. We use the term tautology and contradiction. And typically we use tautology, a capital T, a bold capital T to indicate tautology, and a capital F to indicate a contradiction, something that is always false. Okay, now I did say earlier that I'm going to come back to this. What if I have an expression? Sorry, if I had an expression that had three variables. Okay, so what if I have an expression that involved three variables? Well, let's go back and take a look at this one. So I have P, Q, and R here. I have three expressions. What if I wanted to draw a truth table for P and Q implies R for this statement right here? So that means on the left-hand side, I'm going to need P, Q, as well as R. Now, if we think about it, whenever we had one variable, we had two variations, right? We had a 0 and we had a 1. That's it. When we have two variables, we have four variations: 0, 0, 0, 1, 1, 0, and 1, 1. What about three variations? Now, this is a type of counting problem. So if you want to go back and review the counting problems, I would highly recommend that you take a look at the counting section in order to understand what I'm about to do here. So this is actually an example of a permutation with repetition. So think about P, Q, and R as boxes. Okay, think about P, Q, and R as boxes. How many ways can I fill the box for P? And the answer is I can fill it with either 0 or a 1. Okay, 0 or a 1. That's two choices. What about Q? Also two choices, a 0 or a 1. I can repeat using these objects, and same with R. So the answer is the total number of rows that I'm going to see here is going to be 2 times 2 times 2, which is 2 to the 3 rows. Okay, so in this case, I'm going to see 8 rows. Now, a quick way to come up with all 8 cases is that I know there's going to be 4 zeros for P, and there's going to be 4 ones for P. That's always the case. Same with Q. There's going to be 2 zeros for Q, sorry, 4 zeros for Q, which I'm going to write like this. And there's going to be 4 ones for Q, which I'm going to write like this. Okay, so in the second column, I've alternated 2 zeros, 2 ones, 2 zeros, 2 ones. And then finally, for the final column, I'm going to have 0, 1, 0, 1, 0, 1, 0, 1. And very quickly, we've come up with all 8 cases or 8 variations for P, Q, and R. Okay, so let's take a look at the rest of this expression, or the way that we're going to evaluate the outcome for the truth table here. We have P and Q. So once again, recall what P and Q is. So P and Q is talking about is going to be true. It's going to be 1 when both P and Q are true, but then 0 every other case. So you take a look at all of the cases for P and Q. Both of these cases down here, so you see both of these cases have P and Q equal to 1. So the outcome for those two cases are 1s. Everything else should be a 0. Right? So we have 0, 0, 0, 0, 0, 1, and then 1, 1. So those are, that is the outcome for this bracket in here. Okay, so again, just make sure that you understand what I did there. I'm going to copy over the R. So R is 0, 1, 0, 1, 0, 1. I'm just going to copy this over to the other side so I can see it a little bit better. But ultimately, I want to find out what the final result is. What is the result of this arrow here? Well, the arrow, if you look back at the definition, is that it is true, it is false only when 1 implies 0. Okay, so it's only false when 1 implies 0. Everything else is true. So we actually have that this is a 0 case, so 1 implying 0 is false, but then every other case should be a 1. So this is our final outcome. So we can say this is 1, 1, 1, 1, 1, 1, 0, 1. That is our final outcome for the meaning of this statement. Okay, now let's see if we can pick some meaning out of this. Okay, so what does the truth table actually tell me? Well, it tells me, for one thing, when this statement, this compound statement, is true and when is it false. So if you look back at this statement as saying getting an A on the final exam and doing every exercise in the textbook. So if you do these two things, you get a A in the final and you do every exercise in the textbook, this is going to guarantee that you get an A in the course. Now notice that if I tell you this, this rule, right, this implication is going to be true. It is not falsified under any condition except for the second to last one. Okay. In this case, in the second to last case, you can claim that yes, I did get an A on the final exam, and I did do every exercise in the textbook, and you didn't get an A in the course. So in that case, you can say that that rule is false. Okay, that is the only time you can come to me and say that rule is not true, and I would agree because it has been falsified, right? So think about every other case, right? So every other case, what if you said I didn't do every exercise in the textbook? So let's take a look at the first case. I didn't get an A in the final exam. I didn't do every exercise in the textbook. I didn't get an A in the course. Well, that rule is still good, right? That has not falsified that rule because the first condition has not been met. Okay, so we have to think about that again, and trust me, there will be many times throughout the course that we're going to come back to this argument. Okay, so whenever the the premise, the thing before the arrow is false, that says nothing about the conclusion. It says nothing about the thing after the arrow. Okay, so just try to keep that in mind. Okay, so let's do one last example here, and then we'll go on to the next video. So one way that we can show logical equivalence. Now, remember earlier I said that the biconditional. I said biconditional is the same, logically the same as P implies Q and Q implies P, and it's also logically equal to the negation of P exclusive or Q. So I said both of those things. So how do I show that? How do I show that those two things are logically equal? Well, one way is that we can draw a tabular proof. We can draw a table for both expressions. So here, let's pretend that my intent is to show that these two statements, so these two compound statements, are logically equivalent. Now, notice I said logically equivalent and not equals. Okay, so I can't claim that these two are equal because they're clearly different statements. They're saying not P or Q, and the other is saying P implies Q. They're different statements. Okay, but what we want to find out is the logic that they both represent. Are they the same? Okay, are they the same logic that's being represented? So I'm going to start off with my four cases for P and Q. And I'm going to start out with the second case because by now, hopefully, we remember the chart that we had before, and the implication, the definition for implication is 1101. So once again, the only way that this can be false is in the case where P is 1 and Q is 0. Okay, what about this one on the left hand side here? Well, we have not P, so not P is 1100. So P is 0011, not P is 1100. And Q I'm just going to copy over. Okay, and then I have the not, or sorry, I have the or. Okay, the or says it is 0 only when both sides are 0 and 1 otherwise, right? So false only when both inputs are false, and then every other case is a 1. Okay, so what do we notice about these two tables? Well, right away, we can see that the outcome is identical. So what we can say is that these two statements are logically equal, and we can write this sign, so the equal and then the two arrows on either side, to indicate that these two are equal. Okay, so this is the logically equal. So if we call this A and we call this B, we can say A is logically equal to B. All right. Now, is there an official definition for logically equal? And there is. So let's say that we have two expressions. Now you may have noticed that the logical equal sign, the A and the B here, the logical equal sign actually looks like an arrow pointing both ways, but instead of the one line, we have two lines. We have the equal. So we've already seen an arrow that points both ways. So the question is there a relationship between the double arrow and this logical equal sign? There is actually a relationship between these two. So the thing is that if we try to take A here, if we take A and we take the expression B and we apply a biconditional, take a second to think about what we get. Okay. Now, what is the definition of the biconditional? Definition is that when both sides are equal, when they equal in truth value, then the outcome is one. Otherwise, it's a zero. So would you agree that if I just take A and B here and I apply a biconditional, that it's always going to be true? Right? This is a tautology. This is a true statement. So here is our official definition for A logically equal to B. Okay, so when can I say A is logically equal to B? Well, the short answer is draw a table. And if they match, then they're equal. If they don't match, they're not equal. Right? So that's the short answer. But the longer answer is that I can say A is logically equal to B. A if and only if B is a tautology. So anytime I find that A biconditional B is a tautology, I can say that A is logically equivalent to B. That is the official definition. So again, if I take these two statements, if I take these two tables and I apply a biconditional to it, you'll see that the final outcome is all true. And that's how you know that it's a tautology. That is our official definition of logically equal. Okay, so let me just say that one more time. When we draw a table and we find that two expressions have the same table, exactly the same in every single situation, then we can say it is logically equal. And we use the symbol to indicate logically equal. Okay, so they are logically equivalent. If they differ in even one location, okay, so if, for example, this was a zero, right, but everything else was the same, it would still not be equal. So we would say in that case that the two expressions are not logically equal. So we would use this as our expression. Okay. All right. So now, given that we have this tool now to indicate two sides are equal, to basically represent whether one side is the same as the other, it would make sense to us that there's a whole lot of expressions that are equal to each other. And you would be right. There are a lot of expressions that are equal, that are logically equal to each other. In fact, on the next slide, I've posted a lot of them. Okay, so have a look at this, and we're going to come back in the next video and we're going to start explaining what these things are. So it turns out that these are called laws of logic, and they're very important to what we're going to be doing in this course. So take a look at some of them and see if you can intuitively understand where they are coming from. These F's, this, whenever you see a capital F, once again, is a contradiction. Whenever you see a capital T, it is a tautology. So things that are always false and things that are always true, respectively. So see if intuitively you can see where some of these theorems come from, but we're going to come back in the next video and explain them. Okay, so I will see you then.